Hi, so in this video we are going to go over the limit techniques. However, we're going to break this down. So there's a total of 7 limit techniques, and in this video we are going to go through the first 4 of them. So keep an eye out for the second video in which we'll go over 5, 6, and 7. So let's get started. The first technique, we've mentioned it before, is direct substitution. So this should always be your go-to as soon as you get a limit problem and you want to solve it algebraically. Always go straight to direct substitution. So we see here the limit as x approaches 2 of f of x minus 2 divided by 4x squared plus x minus 7. So direct substitution, I'm going to take this 2 and plug it into all of my x's. There's a total of 3 of them. So I'm going to plug that in. I will get 5 times 2 minus 2 divided by 4 times 2 squared plus 2 minus 7. And once you do that, all you have to do is just simplify. So that's going to be 10 minus 2, which is 8, divided by 4 times 4 is 16. It's going to be minus 5. We get 8 over 11 as our limit. Easy as that. Now, this is when we're going to start seeing examples where direct substitution may not always work. So how do we know that direct substitution did not work for us? That happens when we do that direct substitution, and most likely it's going to be when we have a rational function. So kind of like the function that we did just now here. However, we run into issues when you plug in or do direct substitution, and if you get a 0 in the denominator once you do direct substitution, we know that that means it's undefined. So it means the y value may be undefined, however, oftentimes the limit does still exist. And so when we have an undefined y value, that usually means that we have probably a hole that's happening in the function, which is why when you plug in this x value, let's say maybe this is x equals to 2, you get no output. You get a 0 in the denominator, or you get 0 in the numerator and the denominator. And so we have to try other limit techniques in order to simplify our function in a way that will allow us to still determine the direction in which the left and the right are approaching to, and what would have been that y value had that function been working without a hole. So we're going to look at some of those techniques, some of the different kinds of functions that will lead us to those techniques. So here is our first technique here. Like I said, always try direct substitution. There's no harm in doing that. So I'm going to plug 2 into those 2 x's there, and that gives me 2 squared minus 4 divided by 2 minus 2. Well, that's going to give us 4 minus 4, which is 0, and 2 minus 2, which is 0. This is what we call an indeterminate form. And we can see that up at the top there. Indeterminate form. And that's because we can't really figure out what's going on at that x value. When we plug in, we get 0 over 0. Most likely it's a hole, or it could be a vertical asymptote, some kind of discontinuity, but we still can hopefully find a limit. So the first technique we're going to use is factoring. If I look at this function x squared minus 4 divided by x minus 2, I can go ahead and factor that x squared minus 4 and break that down to x plus 2 times x minus 2. Now here is the first note about limit notation. Whenever you are rewriting a function that you're taking the limit of, you should always keep the limit written out in front. So if I were to have not done that, this would be incorrect notation because we still have not taken the limit of this function. And so we need to keep that notation in front to remind us of what we need to complete and what it is that we're solving for. So we always want to keep that notation as we're simplifying the function. The only time you can remove it is when you actually do direct substitution, which is why we haven't really touched on this notation yet, because so far all of the problems we've done have been solved through direct substitution. So we're going to get to that in just a minute here, but what I've done, so I've factored the top, x plus 2 times x minus 2, and then I can see that the x minus 2's will cancel out. So I'm going to go ahead and rewrite what this would look like once it's simplified. So we see here now we're taking the limit as x approaches 2 of the function x plus 2. And once we've simplified, we can go ahead and go back to the first step, which is direct substitution, and see if it works. Sometimes it doesn't work right away. We have to go ahead and apply more steps, more techniques. But we can see in this case, once we plug in 2 with direct substitution, we get an actual solution 4. So that is the limit of our problem here. Notice notation here. So I have the limit as x approaches 2 when I factored. I have the limit as x approaches 2 when I canceled out the terms. And then I don't have it here once I did direct substitution. So this is what I meant by you must keep that limit notation all the way up until the step in which you actually plug in the value and do the direct substitution, and then you can remove that notation because you've already taken the limit. You've already figured out what the limit is of that portion. So in this case, we can see here that the limit is actually 4. Even though it was indeterminate to begin with, that just means that we have a hole. And if you think back to when we learned about rational functions in pre-calculus, if you were to just look at this rational function here, remember that when you cancel out the terms, that means there's a hole there. So we've found a function here, which is really just a straight line here that has a hole when x is 2. But remember that limits can be holes. So the limit for this function is actually 4 because from the left and from the right, we're still approaching that y value of 4. So simplifying the function algebraically allows us to be able to determine what that value is. So let's go ahead and jump to the next one. And there's a typo in this problem. So instead of x squared, this should be x cubed. So make sure and take note of that. And if I do direct substitution, I plug in 3, that's going to give me 3 cubed minus 27 divided by 3 minus 3. So automatically I can tell the denominator is 3 minus 3 is 0. So that's already a no-no. I know that direct substitution is not the way to go, but we can also simplify the top. That's going to give us 27 minus 27 is 0. So that's even more of a no-no. We cannot have 0 divided by 0. That's, again, indeterminate. So we have to use another technique. So I see x cubed minus 27, and I'm going to think difference of cubes. So again, the technique here is factoring in order to simplify. So the difference of cubes here, we have x cubed minus 27, which is the same thing as 3 cubed. So I'm going to break it down using that difference of cubes formula. You need to look it up. Pause this video, look it up, make sure you know it well, because we will get problems where you need to use the difference of cubes, the sum of cubes, and the difference of squares. So you got to be sharp on your factoring skills there. And this is going to be x squared plus 3x plus 9, all divided by x minus 3. And so we can see now x minus 3 at the top and x minus 3 at the bottom, those will cancel out, leaving me with the limit as x approaches 3. Remember, you got to keep that limit notation. We haven't done direct substitution yet, of x squared plus 3x plus 9. Now this looks like a function that I can go ahead and try direct substitution and see what we get. So that's going to be 3 squared plus 3 times 3 plus 9. And that's going to give me 9 plus 9 plus 9, which is 27. So that is my limit in this case. And we can see again, we had an indeterminate form, and that was due to the hole that exists where x is equal to 3. And we know that's a hole because we canceled out that term x minus 3. So we had a hole in the function, but the limit still exists. And so we can see now that the limit from the left and the right are both approaching 27. So that's our limit here. Our next technique is rationalizing. So oftentimes when we think about rationalizing, we're rationalizing the denominator. That's usually if you have like a root in the denominator, like you have 2 over root 3. We don't normally keep roots at the bottom, so we would rationalize whatever we have down there to give us 2 root 3 over 3 in this case, right? So we have no longer a root in the denominator. So in this case, we are rationalizing. However, our purpose for rationalizing isn't necessarily the same. And so we may at times rationalize the denominator, but we may also rationalize the numerator. So I just want to put that out there so you keep that in mind, that we're not just rationalizing the denominator in every example. It could be either or. So we're really just looking for where is that root, and then that's going to tell us where we have to rationalize. So this example, I can try direct substitution, and I get 9 minus 9 over root 9 minus 3. So automatically that's 0 over 0 indeterminate, so I know I've got to apply some other rule. I look at this function, and I know I cannot factor this in any way. So that's why our first technique doesn't work, direct substitution. Our second technique, factoring, doesn't work. So now we're on to our third technique. We see that square root of x, so I know that I'm going to be able to rationalize this. And what I will do is I will multiply by the conjugate. So I have root x minus 3. So there's 2 parts to this. I got the root x, and then I have the 3. So those are the 2 parts of the conjugate. So I will multiply this by root x, give myself a little more space here, plus 3. All I'm doing is switching this little sign there, because conjugates, remember, are opposites of each other. And whatever you do to the bottom of any function, or whatever you do to the top or bottom of any fraction, you gotta mirror it. So I'm gonna multiply the top and the bottom by root x plus 3. So here's where it gets fun. We've got the limit as x approaches 9. At the top, I have x minus 9 times root x plus 3. I'm not going to worry about FOILing this out, and you'll see why in the next part, why I'm not going to worry about that. So my suggestion to you always is don't FOIL unless you find it's really necessary to. Always try to keep things factored, because then you can easily cancel things out if you need to. Now, when you're multiplying your conjugates, root x times root x is going to give us x. And negative 3 times positive 3 is going to give us negative 9. So we have x minus 9 in the denominator. Technically, we are still having to FOIL this out, do all of that FOILing, but because they're conjugates of each other, those two middle terms end up canceling each other out. So that's why we can just take that shortcut and just kind of multiply those two parts. And from here, we can see x minus 9 is going to cancel. So that is why I said do not FOIL out that numerator. Wait until we can see what happens next. So now we can see we've got the limit as x approaches 9 of root x plus 3. And from here, it looks like I can go ahead and try direct substitution. That's going to be root 9 plus 3, which is really just 3 plus 3 gives me 6. So another example where we had a hole, right? Some kind of a hole here that's undefined, but our limit still exists. So hopefully you're kind of noticing a pattern here in the kind of graphs that will lead to an algebraic function that needs to have more techniques applied to it. We're going to do another example here. The difference in this example is that we have two terms underneath the root. It's not going to really change much, but you just have to be very careful when it comes to multiplying everything out. So again, with the direct substitution, if I do that automatically, right, I can already see I'm going to have a 0 in the denominator. So that's already a sign to me that I cannot do direct substitution. And even more so if I do it to the top, right, that's really just going to leave me with 1 minus 1, which is 0. So we've got an indeterminate form. We're going to go ahead and see what we can do to simplify it. So, sorry, this lighting is kind of weird here. So what we're going to do is look for that root because we can't factor, right? So the root is up top here, and I'm going to have to point out here where the conjugate has to take place, because sometimes it can be hard to tell when we have more than one part inside of the root. So really that subtraction in the middle, that's going to be the part that we change and turn opposite. So we have the limit as x approaches 0 of 1 minus root 1 plus x divided by x. I'm going to multiply by 1 plus root 1 plus x. So notice I did not change what's underneath the square root. It's still 1 plus x. The only thing that I changed was that minus in the middle became a plus. So that is what we call the conjugate of that part. And then we'll divide by 1 plus root 1 plus x. And so now we've got to figure out how to simplify this. The part where we have the two conjugates multiplying, that's going to be where we do most of the multiplication. And remember, the other parts, we like to just keep that factored, and then we'll see kind of what cancels out. So at the top, and don't forget your limit notation, we have 1 times 1, which is 1. And then we have negative 1 root 1 plus x times positive root 1 plus x. So that's going to become negative because negative times positive is negative. And the roots are going to just cancel each other out. So we're just going to be left with 1 plus x. And I'm making sure to put parentheses because this minus will need to distribute through to both of those parts. And at the bottom, we've got x times 1 plus root 1 plus x. I'm not going to FOIL that just yet. I am going to go ahead and FOIL the top part, which will be 1 minus x all over x times 1 plus root 1 plus x And I can simplify 1 minus 1 is 0. And once that goes away, I'm left with negative x at the top and this x term at the bottom. So I'm going to cancel those out. I'm doing this all in one step just to kind of save time rewriting the steps. But that's going to leave me with a negative 1 up at the top. So this will be the limit as x goes to 0 of negative 1 all over 1 plus root 1 plus x. Because that x got canceled out with that x. Those 1s got canceled out, but don't forget that minus there. Now, we've done the work, we've rationalized, we've simplified. Now let's see if we can do direct substitution. So we can go ahead and plug 0 in for x, because that's the only x we have. That's going to give us negative 1 up top, 1 plus 1 plus 0, and negative 1 over 1 plus 1 equals negative 1/2. So it did work out for us. Yay. Maybe not yay to the many steps it took to get there, but we love math, so it was a fun time. This next one may also take a few steps, so let's jump into that one. I can see right away direct substitution is not going to be our solution here, because if I take that 0, x approaching 0, right into the denominator, I automatically get a 0 there. So I know it's going to be undefined, and then probably, yeah, if I plug in at the top, I'm going to get 1/3 minus 1/3. So I know this is indeterminate. So we can't factor it. I mean, at least I can't. And we can't rationalize it because there's no root. But we've got fractions, so let's figure out how to work with our fractions. Since we have two fractions up at the top, our technique here is going to be to find the common denominator just between those two fractions and get those to be just one fraction. So 1 divided by x plus 3 minus 1/3, the common denominator will be 3 times x plus 3. So I'll have to multiply 1 over x plus 3 times 3 over 3, and I have to multiply 1/3 times x plus 3 over x plus 3, just so I can get common denominators between those two fractions. And I'm going to go ahead and keep that x at the bottom. So the reason we don't really touch the x at the bottom there is because we're doing all of, we're really just multiplying by 1 to each of those parts, so we're not really changing it. Okay, I tried to move there to get a little bit of better lighting, but I don't think it helped much. So let's just keep going. The top part will become the limit as x approaches 0 of 3 over 3 times x plus 3 minus x plus 3 over 3 times x plus 3. So we can see there the common denominator, and now we can subtract those together. Notice I have my limit notation still. That's going to be 3 minus x minus 3, because this minus has to distribute. And we've got 3 times x plus 3, all divided by x. So at this point, I'm going to do a little bit of simplifying, because I see actually 3 minus 3, that cancels out to give us 0. So let me rewrite this here. The limit as x goes to 0 of negative x divided by 3 times x plus 3, all divided by x. And so what we want to do is, we have a fraction in the numerator. We need to multiply by the reciprocal of the denominator in order to get these to just become one fraction. So this will be the limit as x goes to 0 of negative x divided by 3 times x plus 3 times 1 over x. That's the reciprocal of our x at the bottom. And these are going to cancel out very nicely, those x's there. Cancel, cancel. We're left with the limit as x goes to 0, negative 1 over 3 times x plus 3. And all we've got to do at this point, since we've done all the simplifying that we can, is try out our direct substitution. So that's going to give us negative 1 over 3 times 0 plus 3, and we get negative 1 over 9. So we do get a solution in this case. We've taken an indeterminate form and we've worked our way towards getting what the limit actually is. And we're going to stop here for this video because I don't want it to get too long. So the next 4 techniques, next 3 techniques will be in another video. So look out for that video.